Assalamualaikum warahmatullahi wabarakatuh and good day. I'm a doctor at Teknikal, University of Malaysia, Melaka. So I do research and at the same time I teach students. My research specialization is in the field of robotic vision, and here I am talking about the emergence of vision in robotics. Let me start with the usage of robotics is still something that haven't been used at large. Gotta start with a bold statement. So in 1997, the world's best chess grandmaster was up against a computer, and the result was astounding win by none other than the computer. It is easy for a computer to process the best moves, while it is hard for a human to do so. But notice that in the second image, it's easy for even a small child to move the piece of the chess, while it is difficult for a robot to do so. Robot is not that good at understanding things in their world, obviously not good at visual perception, and has abysmal hand-eye coordination. So this is the cutting edge research in robotics. When we think about robot, the definition itself comes from a fiction. The way how people see robot at large, like in the movies of Transformers and Star Wars, intelligent being that has the ability to think, move, and even has feelings. They are as well powerful, flexible, and has many forms. While the fact of the matter is, the character is portrayed by none other than us, human, dressed in very mechanical appearances. So that is the irony of intelligent robot. This is the state of the art of robotics. On the left hand side, you can see modern manufacturing of cars. So these robots are fast, strong, they can pick up heavy objects and assemble car without that much difficulty. And it has been there for 50 years. So this is the first generation of robot. On the right hand side, we have Amazon's mobile robot that transfer Amazon products. So the weight is ginormous, the lifting that cannot be done by human alone. So despite that, notice that it still requires the assistance from human, because robot is not that good at recognizing certain things, especially bad at hand-eye coordination. So Amazon employs a lot of people just to move a product from one shelf to another shelf. Suffice to say that it's very hard robotics problem. And although the potential of robot is big, yet many industries haven't really capitalized on it yet. Yes, they had been used widely in factories and logistics, but not at agriculture, environment studies, construction, and many other industries. And this is basically the new frontier for us roboticists that we can put our effort in. So you might be thinking, why is there low penetration on such industries, right? So that's the point I want to bring in the next slide. In any intelligent robotic system, there are three jobs that needs to be completed. It needs to sense the world, it needs to think to make up a plan, and finally act according to the plan. So let's take a look at each one of them closely. First is sensing. For a large part, vision is our most powerful sensing mechanism and critical to almost all of our daily activities. Vision is a wonderful sensor indeed, and we can see things that are far away and we can see things that are up close. It gives valuable information such as color and range of distances. So there are even wonderful quotation from poetry. For example, beauty is in the eye of the beholder, which means the beauty of an object is different from one's perspective to another perspective. And then the second one is, there is nothing invincible in this universe. There's only our lack of eyesight. which encourage us to see the whole world, to venture further. But sadly, most robots can see. So here are the 3 examples that humans do every day with vision. On the left top hand side, we can see a kid trying to solve a puzzle, a jigsaw puzzle. So she's using her eyes to kind of understand the empty spaces that needs to be filled. Then there's a random jigsaw lying on the table that she can use to reason with in order to cover the gaps. Then with the fingers, she can perform some action to kind of solve the puzzle. And another interesting game is Jenga. It gives the mind to pick a piece, what makes the structure stable, and on how to remove the piece safely. So it's quite an interesting game. And going from simple to extreme actions, on the right hand side is some person doing some crazy bike riding looking at the video, you notice that the crazy riding doesn't entirely depends on the vision alone. He's riding there, seeing all the things around him through his eyes, the only sensor in play here, processing that in his brain, and then use his hand and feet to kind of in order to control the bike. So from all this, the bottom line is you can do if you can see. Now here is some interesting fact. Did you know that the brain of a bee is about 1 gram? Only 1 gram, yes. Just by using vision, it kind of know the surrounding, process them using brain. And one scenario could be the bee uses sight to fly in order to find food, basically from one location to another location, sees the flow of surrounding, and land on a flower. So the bee is a very interesting creature, and it has about 1 million of neurons. As compared to us human, we have about 1.5 kilogram of brain and about 10 to 20 billions of neurons to process our vision. So neuron is this one. This one is called neuron. So it is interconnected among each other, and basically it fires millions of signals every second. So it's a wonderful thing to see, and basically a wonderful cell in for a large part of our existence. So on the most fundamental aspect for engineers, there are only 2 schools which uses vision. One is image processing, and the other one is computer vision. Image processing basically deals, given an image, what's the output gonna be. Its processing basically relies heavily on enhancement of pixels quality, and then removing any non-interested features, like for example in medical school, trying to locate the position of tumor in the brain. On the other side is more interesting and much more relevant to robotics, which is computer vision. Basically what's come in, the output gonna be the description of data, and that description of data is concise information of what's inside this image. So this is a crucial information for robot, because otherwise a picture is just accumulation of millions of pixels that doesn't bring anything meaningful. Well, in some cases, a robot wants to know that that is a person, that is an object. So anything useful that the robot can take action on. So computer vision is a critical sensing mentality for a robot. For robotic vision, we need to be able to process that image really quickly, because a robot gonna take action based on it. I cannot take a minute to process a picture. If that is the case, then you can make a coffee while waiting for the robot to move, in which case nobody wants that. So we want an information quickly with low latency, and it needs to be very accurate. Because a robot, when making physical decision based on an inaccurate sensory information, the robot gonna make an error in the physical world. That could be bad news, right? And another important aspect that I want to bring is even if you can be accurate, then at least you can tell me of how inaccurate you are of what you did just sense recently. So in robotics, knowing uncertainty is very, very useful. So in computer vision, recognizing an object has become quite famous when deep learning starts to enter in the early 2010s, specifically convolutional neural network. Just put in massive amount of image for training, then you've got yourself a very powerful vision processor, provided that you have a very powerful computer setup and good algorithm to process the data. So much more valuable insight is to kind of understand the activity inside the image. That will be quite extraordinary because it defines robot understanding level to a high degree, and sometimes an action can be misjudged, right? But most of the time, if a robot is able to understand a course of action above 80%, that is extremely good. For example, understanding that the baby is eating, there's a person jumping, it's cloudy out there, and then there's a person walking, and there's a discussion going on between two people. So that is for sensing, in which the focus was on vision. So the next one is planning. So I know how the world is. I know where I am with respect to the world. I've got a goal. I've got to make a plan in order to get there. And planning is always considered as exercising geometry. So what we are seeing here is the assembly of engine. This problem of solving geometry using robot, which is suitable to match, has always been there for decades. There's wonderful algorithm to kind of solve this problem very, very quickly and very efficiently. But before I go into that, let's talk a little bit about probability. Every planning, there's a certain level of probability, because we know every sensory system is not perfect. Nothing is perfect, but we can say something about how imperfect it is, and then we can reason with it, coming up with a plan which best suited for the situation. And this is one of the most important steps for robotics evolution to kind of increase its capability. They can always have many outcomes, but to say is the outcome optimized is a different matter altogether. So what's really happening right now in robotics is called reinforcement learning. Let's say I would like to program this robot to walk. The traditional way to do that is to write some equation of motion that describe the movement of leg, and then apply physics and math to make the robot stands up or bend 30 degrees, maybe 60 degrees, and so on. And then dynamically we'll consider force and momentum into account, right, for walking. But with reinforcement learning, we don't do any of that. We simply apply a reward function, and we reward this robot if it moves forward and doesn't fall over. And despite of a huge amount of physical simulation over time, now its epoch is 4800, starting to move or starting to walk. Not very elegant, not very graceful, but the reward function can have not only the robot stays upright, but it can move forward for a very long period of time. But perhaps you could say something about how graceful of a motion is as well. This is high gracefulness, high probability of walking with high stability, right? Because it is similar in our case as well. When we try to walk, we don't know the equation of walking, right? We're just learning by experiencing it, and then maybe our parents give us food as a reward, then we can train it to get proficient at it. So that's basically the biological process of how we walk. So this is a new, I would say, new way about programming in robots. We don't think about the mechanism like using math anymore. We do it in simulation. We learn in virtual world. Once we train the virtual and putting them in real world, it's pretty good starting point, and we can do more learning in the real world. This is such a big revolution in robotics. So that is the thinking part. We have done the thinking part. The last part is about acting part. How is it the robot performs some actions? Definitely there's a electrical motor in there that moves stuff. A robot might have propellers, might have legs. So there's a lot of mechanism that a robot could use to kind of move through the physical world. So those are the fundamentals of robotic system. You got sensing, you got planning, and you got acting. Now moving to the emergence of vision, advancement number one, which is about leg robot with vision sensing for inspection. This is called Animal. It has 4 legs. It has the ability to move at industrial environment, even at rough terrain. It has a lot of sensors equipped, and then I just want to focus on the vision aspect, which is for inspection. It can detect the fire extinguisher, the pressure gauge, the gas leakage, or even the cage, right? And over here, notice that it is a quick rundown to check everything works as it is. And although it has a lot of capabilities, there are still room for improvement. For example, maybe you can say, is it robust enough to be exposed to fire? Can it analyze dire situation? Can it be used to find survivors? So those are the top 3 challenges. Let's talk a little bit about flying robots, because this is quite an important advancement of what a robot can do, avoiding all kind of ground traffics. So the flying robot basically has a lot of different shapes and forms. For example, you can have robotic blimp, fixed wing airplane, and helicopters, and so on. So these are a few examples that are currently undergoing for flying robot. There's the one on the left, little flying robot that picked up blocks and putting them into a big complex stack of building. So you can imagine this in construction scenario. It kind of accelerate the construction process. So on the right hand side, there's a simulation of monitoring the battery stage for which the robot can charge its battery. It has its own charging station, right? Its own charging station. So when it is fully charged, it basically can continue on with working what it has left off. So you can use this instead of, for example, crane, right? So there are people exploring various robotics capabilities in the flying robots technology. The top 3 challenges are, what about random lighting condition, can we know the drone health condition, how does it perform when one of the propeller broke down, which is a fault tolerant, and it would be nice to have auto workshop. Next is underwater robot. This is what I did during my PhD years. On the left hand side, there's a simulation from 4 points of view. Imagine that the box which move is AUV. So the task is to dock inside the docking station over here, very small, and without colliding with the station itself. So notice that it can be safely secured into the docking station. From then onwards, it can be retrieved or it can transfer data. On the right hand side is a real experimentation, but it is inside the pool, just proof of concept, and you can see there's a point of view of camera currently doing computer vision stuff to kind of locate the position of the docking station to dock safely inside of it. As for the top 3 challenges, what about random turbulence? Can it go through it? Second, when doing inspection, for example, when you want to inspect the hull of a ship, what about the decision making? And then the third one is underwater charging, which is quite a complex process and interesting research to explore upon. This is the surface vessel robot used for monitoring. These are robotics boats, and we can use this for water sampling in a lake because the water quality isn't the same in all part of the lake, and so it's an interesting work looking at, for example, the methane emission from these kind of lakes, and find the methane bubbles up according to the time of the day and according to the water depth, which is something you would never have found out unless you had a robot that monotonously went around and sampled the water at all points at all times of the day. So this is the sort of the work that robots can do really well, gathering data about the physical world. It can also get the model of the lake, basically what you've seen here, the model of the lake. Once it has done mapping of the underwater part, so this is the mapping, and it can also perform for coastal surveillance such as this. And the top 3 challenges are number 1, what about the random waves? Will it fall over? Which one is the best one between wind and water propulsion? And how about safe tracking intruders? Because when you want to track the intruder, you want to make it at a safe distance, right? You want to know whether it is intruders or maybe someone fishing. That one would be interesting. And this is the last one, all-terrain vehicle, ATV. So the vision sensing is used as well for farming, and you can see here that there's a camera to recognize plant. It use once and then it can use a microdose of herbicide to kind of target where the weed is, and then it's gone. Don't have to spray all of the plantation side. So on the right hand side, there's a manipulator to pick apples, finding the best position to cut and pull the apple. There's a 3D visualization kind of depict the environment. This is using computer vision. And the top 3 challenges, what if the ATV is stuck in the mud? So what is the available option? How to analyze pests in various places, because for chili tree, even if there's a small amount of pests in one day, the next day the whole row got damaged. They require sensitive care. And then how to analyze fruit optimum plucking time. So I just want to end with there is always trade-off of robotic vision. The good are it increase the quality of life. What you see just now, automation farming, there will be less starvation problem. Everything can be done quickly to produce food, and the tech is more durable and efficient. It will increase productivity level from automation, and it can create a new job opportunities like high skill operator to kind of maintain robotic system. The best are there will be privacy invasion. For example, Tesla car has 6 cameras. Imagine 1,000 of them moving in the cities. So you got yourself a whole bunch of data. You'll have limited privacy. Then the loss of traditional job. This has been undergoing for every decades, right? Those who live in the older generation, there's no longer transportation like beca or horse riding. I remember during early 2000s, there are no more bulky handphone. Famous at that time was Nokia 3310, and even now it's gone. And robot army, this is real right now. We already have drone which kill people, drone which uses vision to kind of locate the target and dive into the person and explode. So those are the bad thing from robotic vision. So as an ending, I just want to thank on behalf of the MACE Association for inviting me, especially Prof. Rizal. And I just want to say thank you for listening. And this is my contact information. If you'd like to do some collaboration, you can reach me using email at faid@utem.edu.my, or you can pick up your phone and give me a call at 013-7871-657. Basically, we just want to have networking. Our aim is to try to make a world a better place to stay, right? So thank you very much for listening, and have a nice day.